In this video, we're going to define the cross product of two vectors geometrically. The first thing to realize about the cross product is it inputs two vectors and the output will be a vector. So unlike the dot product, we will get a vector quantity as a result, not just a scalar quantity. The other thing to take note of here is the cross product is something that we do in 3 dimensions. It's not necessarily sensible in 2 dimensions to do cross products. So the vectors that we'll be working with for cross products will be by default 3-dimensional vectors, and the resulting vector will be 3-dimensional as well. So to define it geometrically, I'm going to take u and v to be non-zero and non-parallel vectors in 3D. We'll discuss what happens if they're zero or parallel at the end. The reason why I want them to be non-zero vectors is I want them to have some length, and the reason why I want them to be non-parallel to each other is that I want those two vectors, u and v, to form some sort of plane in space. If they're parallel to each other, the best I can do is kind of form a line with those two vectors, but if they point in somewhat different directions, I get a plane in space that they form. Now, there's an angle between those two vectors. We'll call that theta as we have in the past. And I want to now define what u cross v is. And it's going to be a vector. So I have to tell you 2 things about it. The first thing I need to tell you is what its magnitude is. So we're going to discuss the magnitude of u cross v first. And by definition, it's going to be the length of u times the length of v. The dot product had the cosine of the angle theta. To kind of mix things up a little bit and get something different and interesting and complementary to the dot product, we're going to define the length of the cross product to be the sine of the angle between them, the times the sine of theta. Now the cross product's a vector, so I also need to tell you the direction of u cross v. How am I going to determine that in the picture? And the answer is I want it to be normal to the plane that I've drawn. By normal to the plane, I mean sticking out of the plane at a right angle. So either it's going to go vertically up in our perspective, or it's going to go vertically downwards in our perspective. How do I determine if it should go up or down? And we're going to use the right-hand rule convention to decide. So I'm going to draw in my picture a little right-hand figure there, and it is dependent on the fact that I put u first in this product and v second. So I want you to kind of now do this with me. Just take the fingers of your right hand and run them parallel in the direction of the vector u. Put your fingers of your right hand kind of forming that vector u on the screen there, and then take your fingers of your right hand and curl them inward towards your palm, kind of mimicking that angle theta between them until it gets to the vector v. Pointing towards v, your thumb is going to be pointing up in this picture. If I was to start with my left hand, you then curl towards v, your thumb would go down. So we're using the right hand, not the left hand, to determine that direction. We're going to have a unit normal vector that we call n hat to indicate that direction. According to the right hand rule, it's going to be pointing upwards, normal to the plane. So a unit vector n hat at a right angle to that plane. I start with u, I curl my fingers towards v, my thumb goes up. We can now define the cross product as a vector. U cross v is given by its length, length of u, length of v, sine of the angle. Right now that's just a scalar quantity, and we're going to scale that unit normal vector n hat by that amount, and that's how we define the cross product of these two vectors. I can add that in my picture now. U cross v, if that quantity is somewhat larger than 1, and I'm taking for granted that it is going to be this vector at a right angle to the plane, normal to the plane, and scaling n hat by that appropriate amount. Now, the first thing to notice here is that this is non-commutative. In mathematics, we say that an operation is commutative if the order that you perform the operation in gets you the same result regardless of how you do it. But if I do u cross v, the right-hand rule in my picture dictated that it point up. If I do v cross u, take your fingers of your right hand and start along v, curl your right hand fingers towards u, and your thumb's going to be pointing down now. So n hat would be pointing downwards, and we'd get the opposite vector. So we would get the minus u cross v. So it's a non-commutative product. There's a nice interpretation of this quantity that's scaling the normal vector. In other words, there's a nice interpretation of the length of the cross product. So what I'm doing now is I'm drawing my plane that those two vectors are in, but I'm looking top down at that picture. I'm no longer looking at it with perspective. So that plane now is forming the whiteboard. And I want to find the area of that parallelogram that they form. The area of a parallelogram is going to be the base length here, which I've labeled here as b, times the height of the parallelogram, but that means this perpendicular height, not the side length here that v determines. So the area is going to be h times b. I need to find what h is, and notice that there's a right triangle here involving my vector v. It's involving this angle theta, and it's the opposite side of that triangle, and therefore it's going to involve the sine of theta. So h is going to be, or rather b here, is going to be the length of u, and then h is going to be the length of v, the hypotenuse of that triangle, times the sine of the angle theta, because it's the opposite side that I want. So the area of the parallelogram is the length of u, length of v times sine of theta. In other words, the area of the parallelogram that they form is precisely the length of the cross product. This is a nice interpretation. If I have a very large cross product, then the area that's formed by those two vectors in that plane is very large, or complementary. If I have a very small cross product, the length of it's very small, the area formed by those two vectors is very slim, very little area. Now, what happens if my vectors are parallel or either of them are zero? We're just going to define the cross product to be the zero vector. Zero vector, not the zero scalar. Why does that make sense? Well, if the angle between them is 0, in other words, the two vectors are parallel, then the sine of the angle is 0. If the angle between them is 180 degrees, in other words, they're parallel but pointing in the opposite direction, the sine again is going to be 0, and so the length will be 0. If either of the vector is 0, then the lengths here are 0, and that just makes the entire quantity 0. Just like we did for the dot product, let's look at how the sine of the angle impacts the cross product. And the first thing to observe is if I plot between 0 and pi the sine of theta, it is never negative. So this stuff here is always positive. The directional part is only determined by n itself, by the right-hand rule. Let's think about some extremes here. If I take the angle between them to be pi over 2, so if my vectors u and v are at right angles to one another, then you're going to get the biggest sine possible. And as long as we keep the lengths of the vectors the same, this quantity would be the biggest it can possibly be. And that's because the area of a rectangle is the biggest it can possibly be. If you skew those vectors, open or close that angle without changing those lengths, you're going to change the area and it's going to get smaller. So the cross product here is going to stick out of the plane, and the length of that cross product is going to be the length or the area of that rectangle. If I make the angle between them very slim here, so a very acute angle, that parallelogram is very narrow, that area is very small, and the cross product is going to have a very short length. You should imagine also opening up that angle very wide, making it almost parallel. That parallelogram, again, is going to be very slim, and the cross product is going to be very short in length.